At MIT, we tend to view the world a bit differently than most. Maybe it's our need to see past the obvious, or our dissatisfaction with the status quo. Maybe we're just obsessed with asking the next question and solving the next problem. Whatever the case, we believe that there's nothing in the world that can't be made better, stronger, cleaner, faster, smarter, more life-affirming, life-saving, life-improving. So we discover, teach, ponder, and manage. We build, design, and explore. We invent, innovate, create, and cure. We apply science, and we engineer the future. Because it is exploring and solving that moves us forward. It lifts us. It's what makes the world better. It's what makes us MIT.
Thank you for waiting, ladies and gentlemen. We would like to now start the session for partnership between MIT and AIZAWA for social implementation of energy storage concrete. The program will begin with a press conference on the establishment of the EC3 consortium, followed by the commemorative lecture by MIT professor Franz Joseph Wilm, a finalist for the Cozzarelli Prize, the National Academy of Science Best Paper Award, and a talk session on the theme of the future of energy storage concrete. This will last for about 1 hour. I would like to introduce today's attendance today. And so I would like to ask each of you to please stand up when your name is called. First of all, the host of the press conference. And so Representative Director and President Yoshihiro Aizawa of AIZAWA Concrete Corporation. Thank you. Next. And so from the AIZAWA Technical Research Corporation, Chief Researcher and Senior Fellow, and Mr. Nakamura Seiji. And next, from MIT, and I would like to introduce the members from the MIT. First, Professor Franz Joseph Wilm, professor at Civil and Environmental Engineering at MIT. Next, also from MIT, and so Associate Professor and Admir Masik. Thank you. And next, also from MIT, Professor and Yan Xiaoheng. Also from MIT, Industrial Liaison Program Director of Corporate Relations, Mr. Joanne Bai. So those are the participants for today's press conference. Without further ado, let's start with the press conference. So for those press members, you have already received a press release, so please refer to that paper as well. And so Mr. Aizawa, the president of AIZAWA Concrete Corporation, is now talking about the overview of the today's press conference. This is Aizawa. Thank you very much. Allow me to remain seated. And so 2024 Yuri, at the end of the event, I also talked about this. So today, with the MIT, well, the person sitting next to me is Professor Franz Joseph Wilm, professor at Civil and Environmental Engineering at MIT, and also Associate Professor Admir Masik of MIT. So the research group centering around them of MIT has been working on this project for about 5 or 6 years, or maybe more. And so focusing on the concrete or the cement-based materials and storing energy to turn it into the device to make it as the energy-saving material. So they have been conducting this research for many years now. that kind of concept or idea? Well, the first time I have heard this idea from Professor Wong is about 6 years ago. And Mr. Nakamura was with me back then. And below the dome of MIT, the famous dome of MIT, Professor Wong's the research lab, we have visited there. Back then, it was still just an idea, early stage idea. And so energy storing battery or the concrete or material as be the focus of the project. That was what he said. And it did not, I was not fully convinced, but now it developed so far. And over the years, the research was conducted steadily at the lab. And the year before last, and the result of the evolution was presented at this event, 2023 UE. But now today, this energy storing concrete technology is now ready to put into practice for the industrial applications and so on. In order to transition to that phase, we decided to launch this consortium between MIT and us. We have been talking about this renewable energy and what we produce through the renewable energy, electricity, and by using this basic material, concrete, use it as the energy the storage materials. And we have been talking about this, and we have come to agreements to set up these consortiums to promote this technology. We are going to sign this agreement.
And starting tomorrow, we'll be working together to realize this vision. As you know, MIT represents the collection of the global knowledge and wisdom. It's full of ideas. It's a wonderful university. And in the area of civil engineering and environmental engineering, the state-of-the-art research group and we, AIZAWA, are now collaborating. It gives me the utmost pleasure to be able to work with MIT. And I am very grateful for the support that is given to us. Now, specifics about this consortium. I would like to focus on first the areas that we want to focus on: housing and industrial sectors and infrastructure. Self-heating concrete, early implementation will be the first scope. In addition to that, this application that I'm going to explain is going to take a little more time. We have some panels set up there. This is non-contact EV charging as EV car runs over the pavement. If we use this energy storing concrete as a pavement, we'll be able to charge electric vehicles as it drives. So that is another scope of implementation that we want to realize. And so those areas we have agreed upon. So we will be setting up steering committee. There will be 2 members from AIZAWA participating in the committee. And Professor Ohm and Professor Masick will participate there. And there will be non-voting member who will be serving as a secretariat. So we will set up a steering committee first so that we will be together designing milestones that we want to achieve to eventually realize our vision. So setting up milestones for a joint development and in order to manage the progress of the project. Of course, we have to manage the funding as well. So to do this, specific purpose company will be established by AIZAWA, and we will be running this SPC. Naturally, we will be licensing this technology that is being developed under this joint development. Of course, that is part of our scope. So these are some of the roles that each of us plays. By the end of December this year, self-heating concrete that could be utilized for melting ice, we set sight on implementing this type of self-heating concrete. So we will be starting with this research and development. So after this summer, 2 staff members will be sent to Sapporo for us to be able to collaborate for implementing this technology. Of course, for the details, we'll be working out the details as we go on. But today, I'm very happy to be able to announce our consortium. It's going to be a long-lasting partnership. Thank you, Professor Ohm. So I'd like to invite Professor Ohm to give us a brief comment as well.
Thank you very much, AIZAWA-san. This has been a great honor for us to be with you, develop first ideas from a lab, all the way to thinking now about implementing it here in Japan at a large scale. I'm here with my 2 esteemed colleagues, Professor Yang Xiao Horn and Professor Admir Magic. Our story actually is the story of this project from the smallest scale possible all the way, hopefully, to the scale of implementation. My colleague, Professor Yang, is a world-recognized electrochemist who taught me how you eventually can store energy into concrete. My colleague, Professor Admir, is a world-recognized chemist who taught me how to integrate two materials into one in order to obtain functionality. And I'm a structural engineer, hopefully to make sense out of all this here. So for us, it is a great honor to be here. We're looking forward to implementing this here with the thought that 13 years after Fukushima, a new start has been started here in Japan, in Fukushima, to develop the next generation of concrete technology, which will be able to curb the environmental footprint of the way how we live, moving away from a fossil fuel-driven economy towards a clean energy sector. So again, it is a great honor to be here, and thank you so much for the confidence and the trust which you place in us through this collaboration.
Thank you very much for that. Indeed, we are blessed with the wonderful staffs. Professor Yang, well, January this year, there was a conference in Tokyo. For the first time, I met her back then. And so I was very impressed by her lecture. She's so smart. I was very much impressed. So after her lecture, and then I chased her and then had time to talk with her. And we found out that she is one of the members working on this project together with the Professor Wong and Professor Obasik. And I was very surprised to find out about that. So, but that was a wonderful surprise. So shall we move on to the signing of the agreement? Yes. And so now we heard from the AIZAWA-san and Professor Wong. So let us move on to the signing ceremony of the agreement for the establishment of the consortium. So please prepare for the signing. Thank you. So after the signing ceremony, we will have a commemorative photo session. Of course, the press members, you're welcome to take a photograph at the moment too. Now the signing ceremony is finished. So let us move on to the photo session. So those members who are on stage, please stand up. And so please line up behind the table so that we can take pictures. And so please keep the agreement. Please hold the agreement in your hand. And so Professor Masik and Professor Yan and Mr. Bai, could you move closer to the center? And so let's take a photo. So for those press members who would like fans to look at your way, please raise your hand and they can look at you. So the person who are standing in the middle wearing black, so in the center, please look at the center. Yeah. Anyone else? One. And so on the right-hand side, to your right. Thank you. Thank you. I believe it is about time to wrap up the photo session. Thank you. I'm sorry, it's okay? Okay, thank you. So please give them a big round of applause. Thank you. And so please be seated. Thank you, Professor Wong. And so next is a Q&A session. And so in a press release packet, and you also find the list of questions. And so for those who have questions, please raise your hand and we'll bring the microphone. Please state your name and your affiliation, and also identify who you are asking question to, whether it is to MIT or AIZAWA. So please raise your hand if you have any questions. And so, Mr. Kurosawa. This is Kurosawa from the weekly blog. I have questions to Mr. AIZAWA. And so you're going to start with this project for now. So the image that you have about the EC3 consortium, especially the application for the residential housing. For instance, it's going to be used for the wall materials to generate power, or the image that you have for the actual implementation. If it's going to be used for the housing, meaning that the trading house or the house builders, I think you need to collaborate with them. And so I'd like to know your concept and also the mechanism that you're going to build to make it happen. And so you talked about the housing, residential housing. Well, the market, the residential housing is a very area where we could easily to explain about the social implementation. For instance, the PV panel is attached to the roof of the housing. It could be used as the energy storing, and also the base foundation for the building. Whether that is going to be used for the foundation for the housing, or could be used for the structural or non-structural materials. It could be used for both, or it could be sandwiched. But this cement and energy storing and can be put it into the foundation of the housing. So a zero emission housing can be achieved by using this. And so I believe this will lead to the breakthrough. So the residential market is the highest potential, and also within this market, residential segment. And so applying a very mild electricity, and it can be served as the source for heat. So it could be served as a heating purposes. So of course there are other restrictions, but the energy storing function that will increase the functionality or performance of the concrete. So the concept behind EC3, for those who are interested in, well, there are many house builders who have shown interest in this EC3. That is why we set up this consortium. Consortium is not just about the MIT and AIZAWA. For the purpose of popularization of the technology, of course, we can welcome new partners. And of course, this consortium is expandable and it can be expanded, scalable. So we are flexible on that. Thank you.
Thank you very much. Due to time constraints, we can only take one more question. Does anybody have another question? Yes, please go ahead. My name is Hyuchi from Japan, Nihon Keizai Shimbun, Japan Economic Journal. I have a question to Mr. Aizawa. Now, this energy storing concrete social implementation, well, when do you think this can be socially implemented? And you said you will be setting up SPC. When do you want to establish this SPC? First of all, as I said earlier, this year, by the end of this calendar year, the end of December this year, we have brought a demonstration machine how we can use concrete as self-heating material. And in Hokkaido, more specifically, we will be implementing that, and we should be able to demonstrate how this is really implementable, viable, and feasible. And Japan-US research team will be formed to demonstrate that. That will be the first milestone. And after that, as I said, what market are we going to aim for? We will examine priorities and then design following milestones. Of course, development requires funding, so we will be designing milestones. And to manage those milestones, we will have to set up SPC as quickly as possible to manage budgeting. So our wish is to set up SPC as soon as possible. Thank you. Due to the time constraints, we're sorry to close the Q&A session for now. Thank you very much for asking questions. Now we would like to move on to a commemorative lecture by MIT professor Franz Josef Wurm, finalist for the Kotzarelli Award, the National Academy of Science Best Paper Award. Kotzarelli Prize is a prestigious award that recognizes papers that reflect scientific excellence and originality. So, Professor Wurm, please take the floor. And Professor Masick as well, please come here for demonstration as well.
Thank you very much for having us here. We have been a couple of days now here crisscrossing Japan precisely to address the question, with whom are we going to implement this beside AIZAWA concrete? But today we are here to show you actually what already works as a benchmark, so that when we come back in a year's time, or you come back in a year's time, we can show you where we reached with this project. So we all know what this is about, right? We all know that today we need to address the environmental footprint of our mobility. We have to address the question of how we transition from a fossil fuel-dominated economy to an economy based on renewables. And this transition needs to be competitive, meaning possible for everyone to participate in. But what we need then, in essence, is we need that every building is a battery for energy storage. We need windmills which need to operate at levels much higher than they operate today, because otherwise we would need to make the entire coast of Japan full of windmills. And we need, of course, roads which are self-charging, and we dream on and on and on, all what we need, and don't know how to get there to this energy transition. So what is the problem? Why can't we not just jump out there and do it? The problem is straightforwardly understood if you think about what the fossil fuel actually is. Fossil fuel combines the energy source and the energy carrier in the same place, which is different from renewables energy, where the energy source, electrons, and the energy carrier are separately, which is why we need to store energy intermittently to meet the difference in time between demand and supply. Just think about it when you have a photovoltaic cell, and a photovoltaic cell works when there is sun. At nighttime, you wouldn't have this energy. So there is this need to address this question of intermittent storage. So if we want to reach there, we need storage capacity today, which bypasses what we have currently available in form of battery, existing technology. We need a technology which is everywhere. And since you know that we are academics, I will ask you a question. What is the material most consumed on planet Earth? You can say it in Japan, I will get a translation of it. It's water. But after water, the second material most consumed is concrete. So ideally, what we would like to do is we would like to use every wall, every column, every beam in this building for energy storage. But that is not possible, not with the current technology. And the reason is that concrete is based on oxides. And oxides cannot conduct electrons. So there is no way that we can translate concrete from its pure strength capacity, for which we use it in buildings, towards an energy storage capacity. And we all know why we love concrete. Just think about the last earthquake, which you may have witnessed, and where you appreciated the strength of concrete. But not so fast. We actually can do something about it. In fact, we can add into concrete carbon black. So in essence, some refined form of charcoal, which we mix up with cement, a little bit of chemistry to get it workable, and water in order to form an electron-conductive concrete. Electron-conductive concrete. And why does that work? Well, first of all, just here this graph, and I will not show many graphs, but that's a very important one. Resistivity, which is the opposite of conductivity, resistivity of a normal concrete, you see here, is on the order of 10 to the power 7, 10 to the power 8. But when you add a little bit of carbon black on the x-axis, down on the x-axis, when you lift just a little bit of carbon black in 2.5% of weight of cement into the material, out of a sudden you see that the resistivity drops by 8 orders of magnitude. The material becomes electroconductive. Now that is a huge surprise, but how does that work? Well, if you put carbon black in water, it will clump. It will be actually held together by water forces, van der Waals forces. But if the same water is consumed by the hydration reaction, by the reaction of cement with water, well, what you then obtain is a volumetric wire going throughout the material at a mere 3% or 2.5% of carbon black inside the material. Now, and then you can start doing things. Well, the first property is to what AIZAWA-san already referred to before to as the self-heating. Well, actually, this self-heating is nothing else but the experience of a stove. And here, my colleague will just show you how this stove actually looks like here, or concrete stove here. You see here, well...
Yeah, okay. So you see the slabs that are basically charged with a very small voltage. These electrodes are eventually produce a flow of electrons through the slab. this flow, eventually, electrons have resistivity to go through the material, and like a stove, like a Joule effect, you have a heating of your material. And you see, I don't know, on the camera, if you can see, for example, this one is quite hot. This one is quite hot. I intentionally turned off the third one here that has no voltage, and you see it's very cold. And then next one is hot, next one is hot, next one is hot. Okay, so here, cold, hot, hot. Just because we have a complete control of which one we turn on.
So this is the stove.
We are going to put some ice on one of these.
Okay, so he will put some ice on it to show you that it is melting. But the most important thing about this here is this is just achieved by adding 3, 4, 5% of very cheap carbon black inside the material. So here you see now the melting of some ice. And hopefully by the end of the year, we're going to have this effect in Sapporo. Right? Okay. Let's continue. Let's continue with the presentation. Can I have back to presentation? Yes. So here, you see this was this 2-meter section, so that technology already works. You see here different voltages applied, and here is sort of a thermal image of this effect of voltage on temperature rise. In essence, the temperature increase scales with the voltage to the power 2. But that's a straightforward application. But now let's go from this so-called Joule effect, self-heating, to energy storage. We already know why it is important. And what is the issue here? Right now, the lithium ions, which is the main ingredients for modern battery technology, is processed, 90% of it is processed in China and very locally. So if we want to scale such a technology to the scale of, well, the world, we wouldn't be able to do this because it's just concentrated 90% in one country. So what we need is an alternative to it using chemical precursors which are everywhere available. And here an example of distribution of carbonate minerals. Carbonate minerals is the base material for the production of cement. So what are we talking about here? We're not talking about batteries. And if there's one thing I hope you leave today with is that we are not talking about batteries. Batteries do the following. You change electrical energy into chemical energy, and when you need it, you bring it back, which is why the efficiency of batteries is very rapidly declining because of this energy change from electrical energy into chemical energy and vice versa. What we are talking about is a parallel technology which is well used, for instance, in all electric vehicles or hybrid vehicles, which is called supercapacitor. In contrast to batteries, rather than having a chemical reaction, when an electrode is polarized, meaning charged positively or negatively, then ions which are in the pore solution attach to the electrode, and they stay there as long as the electrode is polarized. In the moment when you take it off, you recover this same energy. So that's the principle of a supercapacitor with a separator in between. So we apply this here exactly, this technology or this foundation of electrochemistry, we apply this here to our cement carbon electron conductive material with the following 3 ingredients. 1, a volumetric wire, which is our carbon black network, which is created in the material. 1. 2, a pore space, which is naturally in concrete, which is the host for the electrolyte. And the third is the storage porosity inside the carbon black to host the ions for energy storage. These were our first systems with which we came last year here to Fukushima. Now you see here a 12-volt system, which my colleague will explain to you now. Yes.
Microphone. Okay, yeah. So first of all, let's have a look to the ice, okay? Here the ice we put on the stove, concrete stove, is melted at this point. So after a few minutes, that's good. So self-heating occurred. But here now we have a 12-volt supercapacitor made just of units like, okay, so these plates that are plates made out of cement and carbon black. And if you put them in series like this, you can achieve the voltage. And here I'm gonna use photovoltaics to basically charge this system here. You see, you connect it, and it's charging. Let's say this is the day, okay? Now it's the day, and our concrete supercapacitor is charging. And when the night comes, you don't have a light anymore, okay? So now we hope we store this energy from the photovoltaics into our system. So I will disconnect it, okay? Disconnect the photovoltaics. I will basically turn on supercapacitor, good. I'll try to use a Game Boy, okay? Without batteries, with this disconnect. I'll disconnect this one as well. This is just to measure things. So this is independent system now. And if I turn on Game Boy, it should turn on. And I can play games, okay? Okay, in theory, so this is just a USB. See, I just disconnected. So USB, and it's back on. And you see, it's completely independent system based on the cement supercapacitor, cement carbon black supercapacitor.
So, please, if there's anybody here who has an empty iPhone to charge, please bring it forward. We're happy to charge it here on the supercapacitor. Okay, so you have seen how this principle goes. It's actually pretty easy. All what you have to do is you take cement, you take carbon black, you add water to it, and you create electrodes. And now this here is just a prototype system, if you want, of something which you can fill up the space in a column, right? So every column actually becomes a host for these supercapacitor systems. And then you can imagine that in a home, as you see it here, photovoltaic cells on the roof, a system which is like this one here in all columns, eventually in the foundation, in the beam structures of your home, so you should be able to reach energy independent of a singular home. To give you an idea about energy density, what you would need to store the energy demand for one day of a home, for a whole day, you need 40 cube meters of this electron conductive material. 40 cube meter is in essence the foundation of such a medium-sized home, which would be sufficient in order to store the energy demand. But when I now go through any building, and like this beautiful concrete building here, I look at every column and say, oh, wouldn't that be nice to have the energy here? And it would be alimented by photovoltaic cells or windmills. So you see here these small systems here as they go along. Just want to make the point here, this is right now cement and carbon black. But we already showed that if you add sand to it, which becomes mortar, it works as well. Or ultimately, what we hope to achieve in this upscaling project, in this EC Cube project hub, is to use it all the way to concrete. So you saw here these iterations around the system. So then you understand that in essence, this idea of an energy storing solar-powered building is not something which is science fiction, but it can actually be done with materials everywhere available and done by bringing together, well, the homeowner who needs to want it, together with the right material producer, structure producer, and the builder in order to create an energy transition for residential and industrial buildings. By the way, when it comes to windmills, just consider the fact that windmills today operate at an efficiency of maximum 30%. And that is due to the fact that windmills, the wind spikes which happen, cannot be stored into batteries because it's too fast. These spikes occur too fast. However, if you use this type of material, which supercapacitor technology, which allows you to extremely fast store energy, I think it will be possible to increase the efficiency of windmills from 30 to 80%. A last word about self-charging roads for electric vehicles, the dream or the nightmare, or to overcome the nightmare of anybody who has a pure electric vehicles. And you should thank Toyota and others for having developed the hybrid car. At least you don't have to worry so much about it, right? So what is this idea about how does that work, this technology? It's in essence very similar to you charging wirelessly your phone. The principle behind it is that you have two electric fields, one in the car, which already exists, and another one in the pavement. Electric field requires that you have electron conductivity. Now, if we are able to get a high enough frequency of current in the pavement, then we are able, by electromagnetic induction, to transfer charge from the pavement into the vehicle. So that's still to be shown. That's why this project is also a project of research and development. But ultimately, that is behind it, and hopefully next time we meet, we will be able to show you not only a self-heating pavement, but one where maybe a small car can already drive. And that brings me to the closure of my talk about this here. Think about all what this type of technology actually holds in it. If you look at each brick and you consider that each brick is nothing else but one of these supercapacitor here, you can imagine how much energy you can store in a building. But also think about the innovative ways of producing concrete, which you can see here at AIZAWA Concrete, 3D printing. We can imagine that we can print actually these electrodes using the same equipment which you can see outside right now, of course, without carbon black in them. So what that holds actually here, a transition, an energy transition, which will ultimately lead to good paying jobs. It will ultimately lead for everybody to participate as individuals, but as a society as a whole, in this necessary energy transition and curb the environmental footprint of our mobility, of us living in comfort. Thank you very much.
フランスどうもありがとうね。はい、ちょっと時間ないから
Thank you so much. Thank you so much, Professor Ohm. 3D printing has been mentioned. It's production technology and that core technology. By combining these two different technologies, we'll be able to scale up the implementation. It's a very good example. So we were discussing that over dinner. We talked about 3D printing concrete. And with regard to this technology, utilizing 3D printing, so do you have a sort of a plan or any plan for actions in this area?
Yeah, I mean, 3D printing is something that opens the design space for us. Instead of pouring concrete into a form, brings us into a position to create completely unexpected forms, which then will be required to maximize, for example, the efficiency of the multifunctional systems that we are designing in our labs. So it's completely new dimension that is open for us, and we can't wait to put our hands on this completely unexplored space.
はい、ありがとう。この 3D と合体した時の
So utilizing 3D printing, I think there's a great potential. Now, Professor Yang, you haven't spoken at all. Do you think what Franz said is correct? Do you want to check the accuracy of his information? When this is implemented, beyond that, what are some of the future possibilities beyond implementing the technology that we discussed? Your image, your vision, please.
So first I want to say it's my great pleasure to be here, and it's really great to learn about concrete science and engineering, and I think it's really exciting time because we're going through a paradigm shift, how we think of concrete and the future of concrete. Right? So, for example, multifunctional concrete, right? Through 3D printing, we can bring electrons and ions to really enable a number of properties, a number of functions that we could not imagine. We just showed 2 examples, but I think this is the very beginning, and just during this trip, we have really envisioned many possibilities of, for example, looking at, think of using concrete to think about utilizing, take advantage of the low cost and take advantage of the cost. So can we think of concrete to capture CO2? Can we think of concrete to significantly develop negative carbon technologies? Can we think of concrete in what ways that we can store more energy to develop concrete, to create, for example, new art forms? So these are really possibilities, and we cannot wait to getting started or only limited by our imaginations. Thank you.
はい、どうもありがとう。最後
Thank you, Joanne. So 6 years ago, Franz and us met for the first time, and so he was the one who introduced us. So Joanne is like a matchmaker. So thank you very much for your introduction. So the front, Professor Franz, a commemorative lecture was just delivered. Kotsareri, what was the name? Award? Yes, he was a finalist. And so National Academy of Science, the awards, the finalists was what this is all about. So it was wonderful. It's just one small step before the winning the Nobel Award, I guess. And so while we are discussing about this, it came as a very good surprise, and I learned this from Professor Yan. So congratulations, Professor Wong, for being a finalist for that. So with the press with the time, I just wanted to ask everyone to give a big hand of applause to everyone who made a presentation contribution today. Thank you. Of course, we wanted to hear more from them, but unfortunately, we ran out of time. So I hope you learned a lot, and we had a demonstration as well, not just a lecture. And so that will redefine the principles of concrete. So please continue to watch what is going to happen. And so with this, we would like to end this section for the collaboration between MIT and AIZAWA for the creating and making this an energy storage concrete reality. Thank you very much for everyone, and also please give all the speakers another big round of applause.